Good morning, everyone. First of all, thank you, Clay and Scott, for this great opportunity to present first project of my postdoctoral fellowship work in Dr. Heather White's lab at University of Wisconsin-Madison. So today I would be presenting a data, which is basically meta-analysis to determine the effects of supplemental hormone-protected lysine during the lactating period on performance and amino acids profile in dairy cows. So as I mentioned, that lysine and methionine, they are the most limiting essential amino acids, especially as we know that the diets of dairy cows are primarily based on corn or soybean. So those amino acids are deficient in those ingredients. And lysine contributes almost 9% in the milk protein, which makes it a crucial nutrient to balance in the diets of lactating cows. Traditionally, we use many different sources to balance the essential amino acids, and one of that is supplementing blood meal. But due to the different processing technologies adapted in the blood meal, and also in some part of the world, blood meal is not used. So using supplementing hormone-protected lysine as a source of balancing lysine in the diets is used. But one of the issue with the lysine is when we use as a blood meal, it has to go through the heat process, which reduces its digestibility. And also the feed ingredients such as cottonseed meal, soybean meal, or whole soybeans, they also tend to reduce levels of lysine because of this reduced digestibility. So up till so far, most of the studies which have reported the effects of supplementation of hormone-protected lysine, they show quite variability and inconsistency in the results. And part of the reason is whatsoever studies have been conducted so far, 30% of studies had only 15 or more experimental units per treatment. So which tells that not many of the studies were conducted using large number of experimental cows, which could be one of the reasons for the variability in the experimental results. So previously, we have been using the guidelines which were recommended by NRC, and those guidelines were balancing lysine and methionine at the rate of 7.2% and 2.54% of metabolizable protein. But recent recommendations from NASEM, they suggest a bit higher concentration of lysine, approximately 7.6 to 7.8%, and which suggests that there is a need to reassess the values required for balancing lysine and methionine in the diets. So there has been only one meta-analysis, which was conducted back in 2010 by a group of Dr. Robinson. And in that meta-analysis, they had only 12 treatment means, which suggests that not most of the data was available at that time. So there is a need to update the analysis, which should incorporate the last 14 years of research work to get more insights on the supplementation of hormone-protected lysine. So with that background, we hypothesized that supplementation of hormone-protected lysine during the lactation period will improve the performance in dairy cows. And also applying mixed models meta-analysis, it would result to identify the optimum concentration of lysine in the metabolizable protein to improve performance in dairy cows. With these specific hypotheses, there were three objectives in this meta-analysis. So one of that was to determine the impact of supplemental lysine when fed as hormone-protected lysine starting from the postpartum period on productive performance and amino acids profile in blood. Second objective of this meta-analysis was to identify the optimum concentration of lysine as a percentage of metabolizable protein supplemented to lactating cows. And Third objective was to see if the response to metabolizable lysine as a percentage of MP depend upon these postpartum supplies of dietary methionine. So in this meta-analysis, we first of all set an inclusion criteria, and this inclusion criteria involved that we would only have randomized experiments, which were either complete randomized design or randomized complete block design experiments. Those experiments must have a reported experimental unit, which could be cow or pen, and it has to be defined in the manuscript if this information was not clearly stated. So we contacted authors to confirm this thing. The second criteria was that every experiment must have a control group, meaning that no supplemental rumen-protected lysine should be in the diet of that group. And the second group should be a treated one, which can be either based on one or multiple levels of lysine supplemented as rumen-protected lysine. Next on, we had an inclusion criteria that whatsoever product representing rumen-protected lysine was used in particular experiment, it has to report the concentration and intestinal digestibility so that the amount of metabolizable lysine coming from that rumen-protected lysine product can be calculated. And also rumen-protected lysine can be used as a component of either TMR or it can be top dressed in those manuscripts. Lastly, we wanted to have the ingredient composition of postpartum diets, which were fed in that experiment, since several platforms are used to formulate the diet, such as NRC or NISM or some other CNCPS. So we wanted to make sure that we constitute those diets. So we wanted to enter those diets in the same platform. In this case, we used NASM so that the duodenal flow and the estimate of the nutrients can be optimized using a single platform. So for that, we needed to have the information on the diets of the postpartum during the postpartum period. And lastly, experiments had to report least square means and measure of error of individual treatments for the responses of interest. So initially, we conducted a literature search starting from 1990 to all the way to 2023. The reason we chose 1990 because when we were doing literature search, I guess 1990 was the first year when an experiment based upon our eligibility criteria was reported in the literature. So in order to do literature search, we used 4 different search engines. So one of that was PubMed, Web of Science, and then we also looked into the proceedings of Journal of Animal Science and Journal of Dairy Science. We used a certain keywords to identify the manuscripts based on our inclusion criteria, and those keywords involved lysine dairy cow, lysine transition cow, rumen-protected lysine cow, or rumen-protected lysine transition cow. So the reason we use transition term in our keywords was because we wanted to identify those studies which might have applied factorial arrangements of treatments during the transition period. And in this particular meta-analysis, we wanted to compare not what happened in the prepartum period. So if the prepartum interventions are similar in 2 groups, but both groups, they differed with reference to with or without supplementation of rumen-protected lysine in the postpartum period. So that manuscript was counted for this meta-analysis. And also, whenever we needed some information and it wasn't available in the manuscript, so we contacted authors via email. And most of the time, we received a response on that information to clarify before we did our analysis. So let me walk through this Prisma flow diagram just to give you an idea about our literature search. So initially, based upon those keywords and in the search engine which I mentioned previously, we identified close to 7,000 articles. And since we used different search engines. So it's possible that similar articles pop up in different search engines. So we had to remove 4,351 articles because they were duplicated. And then we started our screening. So as a result of screening, we had to exclude a little over 2,500 articles because either those manuscripts were not they were not related to our inclusion criteria, or those work were reported in other species, or that work was done in vitro. So we removed those manuscripts, and then finally we found 43 manuscripts, which by looking at the title or reading the abstract, we thought that they might fit our eligibility criteria. But when we went into the detailed section of materials and methods, unfortunately, 31 manuscripts did not qualify. And finally, we had 12 manuscripts involved 13 experiments which fit to our eligibility criteria. The major reasons for these 31 manuscripts were either those experiments were done with the lysine infused in the abomasum, or the source of human protected lysine was not protected. And also many of those experiments used crossover design. It is possible to use crossover design in this meta-analysis, but we just did not include those manuscripts in this meta-analysis. So in this analysis, like I said, we had 12 manuscripts and 13 experiments, and these experiments had 40 treatment means, and the data was based upon experiments, but it involved 594 multiparous lactating cows. So we collected some information which was going to be part of our model. So we wanted to know what breed, what was the design of the experiment used in the individual manuscripts. We wanted to know the ingredient and nutrient composition of postpartum diets. We collected that information. We also collected rumen protected lysine product, which was used, not only rumen protected lysine, but also rumen protected methionine product, which was used in those manuscripts. And we calculated the amount of metabolizable lysine and methionine supplemented in the diets of those experiments. And also we looked into the duration of feeding rumen protected lysine in the postpartum period. We collected information on our responses of interest. In this case, our responses of interest was intake of the cows, body weight and body weight change, productive performance, feed efficiency, and concentration of amino acids in blood. So regarding the mathematical approaches to analyze the data, we used two different approaches. The first one was where we wanted to address a simple question: what happens when you feed or you do not feed rumen protected lysine in the diets of postpartum cows? So for that approach, we handled rumen protected lysine as a categorical variable, not supplemented versus supplemented, and we put that as a fixed effect, and we weighted the individual comparisons or the experiments according to the standard deviation and number of experimental units to account for the % of each experiment, meaning that the experiments which were done with more number of cows, or experiments which were done which were precisely done, they would carry more weight in the analysis as compared to the other ones. And the second methodology that we adapted was to apply the mixed effects meta-analysis to determine the optimum amount of lysine as a percentage of metabolizable protein. And for this, we used mixed procedures of SAS. And in this case, we weighted the inverse of SCM squared to account for the % of each experiment. And the model was a fixed effect of lysine as a percentage of MP, either linear and quadratic effect, and then fixed effect of methionine as a percentage of MP, and interaction between lysine and methionine as a percentage of MP. And whatever approach we used, all of those models, they included the random effect of experiment. So this table, I'm sorry if it looks too busy, but I just wanted to make the case that this is the diet of control cows, which were not supplemented with rumen-protected lysine, and we had 17 treatment means in this group, or rumen-protected lysine group, where we have 23 treatment means. So we, like I said before, we used the ingredient composition, which was reported in the manuscript. So we used that information, we entered those values into NASM, and then we predicted these nutrient intake and duodenal flow based upon NASM. So you can see here the diets between control and rumen-protected lysine groups in terms of net energy of lactation, crude protein, metabolizable protein, net energy of lactation intake. They look pretty similar, but the major difference was in the control group. You see there is no supplementation of rumen-protected lysine, whereas in the rumen-protected lysine group, the amount of metabolizable lysine after adjusted for the concentration of lysine and digestibility of lysine of that particular product, the range was somewhere between 5.1 to 40.6, with an average of 19.3 grams of metabolizable lysine was supplemented through rumen protected or encapsulated source, which took the overall the lysine metabolizable lysine content from 140 to 160 grams per day. And similarly, if you look into the lysine concentration of lysine as a percentage of MP, it went from 7.0 to 7.6%. So clearly, the diets of rumen-protected lysine-fed cows, they had increased concentration of lysine for during the postpartum period. So going towards the results from this meta-analysis, so like I said, we used two approaches. So this forest plot, it comes from the first approach, where we just wanted to know what happens when you feed or you do not feed rumen-protected lysine in the postpartum period of cows. And here you see a subgroup analysis, because in our data set, we found two cohorts. So one cohort of studies where the supplementation of rumen-protected lysine started in the early lactation. And we define early lactation whenever the supplementation of rumen-protected lysine was started in less than 90 days in milk. We categorize those experiments as early lactation group, or whenever the rumen-protected lysine supplementation started after 90 days in milk, we categorize that group as mid-lactation group. So this forest plot, if you go to the left side of this forest plot, so every reference is a treatment comparison, meaning that every row is a comparison between a control and a rumen-protected lysine treated group. The central black line represents that there is no effect of the dietary intervention. In this case, is rumen-protected lysine. And then the maroon or the reddish dotted line suggests that there was an effect to the dietary intervention. The black dot here is the effect size, which was estimated based upon original scale. In this case, is weighted mean difference. If the black dot moves towards the right side of this black line, it means there was a benefit to the dietary intervention. In this case, we have milk yield as a response of interest. So you can see if the black dot is moving towards the right side, it shows that there was an increase in milk yield. If the black dot is going towards the left side, it shows that there was a decrease in the milk yield for that comparison. The gray square or the gray box around the effect size around that comparison reflects how much weight of that comparison was involved in the statistical analysis, and this has also been reflected in the right column. You can see here the weight of that particular comparison in percentage here. The central black line, it represents the 95% confidence interval, and this diamond shape symbol reflects the overall response of supplementation of rumen-protected lysine on the milk yield. So you can see here, whenever rumen-protected lysine was supplemented in early lactation, the overall response to the milk yield was an increase of 1.5 kilograms of milk yield per day. And based upon this I-squared, which is a marker used for the heterogeneity, so we did not find any heterogeneity in the data, suggesting that the response is consistent across those comparisons. But whenever we ran this exact same analysis, and for the mid-lactation cohort, and you can see here, there is a still benefit for the supplementation of rumen-protected lysine for the milk yield. However, the magnitude of response was a little bit reduced, and there was an increase of roughly 2 pounds of milk. But overall, if you combine all of the data set, which comprise 40 treatment means, there was an increase on the milk yield, and the benefit was 2.2 pounds or 1 kilograms of milk, an increment in those cows which were fed with rumen-protected lysine. In another analysis, we categorized those experiments where the duration of feeding was more than 70 days or where the duration of feeding was less than 70 days in milk for rumen-protected lysine. And you can see here, whenever rumen-protected lysine was supplemented more than 70 days after CAVI, the response was greater, and it was close to 1.5 kilograms per day. And whenever the duration of feeding of rumen-protected lysine in the postpartum period was less than 70 days, the response, there is a still benefit of the intervention, but it reduces. And overall, it's the response to increase milk yield for the rumen-protected lysine supplemented cows was 1 kilogram. So suggesting that when it comes to supplementing rumen-protected lysine, it seems that cows which get rumen-protected lysine or which get balanced lysine in the ration early in their lactation and for longer duration, they get most of the benefit for this intervention. Now, for the other set of analysis, we wanted to see what is the optimum amount of metabolizable lysine as a percentage of MP for our responses of interest. So let me just explain you one scatter plot, and so that you can have an idea what are those symbols representing and what are those lines. So here we have a graph for the dry matter intake. So on y-axis we have a dry matter intake, and on x-axis we have metabolizable lysine as a percentage of MB, which range somewhere from 4.5 to 9.25. These triangles, they represent individual experiment, and the treatment means within the individual experiment, they are connected by those dotted lines. The size of these triangles, it is based upon the weight of the experiment. If the experiment was done with more cows, or if the experiment has less standard error of mean, if the experiment was precise, it get more weight as compared to those experiments which were done with smaller number of cows or which had a lot of variance. So you can see here, and on the top side, if there was an effect of lysine as a percentage of MP, and this is a beta coefficient suggesting that an increase of metabolizable lysine from 5 to 6 increases or decreases this many units in the response variable. So you can see here, we did not find any effect for metabolizable lysine as a percentage of MP for dry matter intake. However, in case of milk yield, we found a linear effect of lysine as a percentage of MP, suggesting that there was a linear increase in the yield of milk up to the point of 9.2% of metabolizable lysine. So an increase from 5 to 6% of metabolizable lysine increases this many units or 0.96 kilograms of milk per day. We also observed the similar trends as we experienced for the milk yield. for milk fat yield and milk protein yield, we observed a pretty much linear response for those response variables, suggesting that supplementation of lysine not only supports the synthesis of milk, but also it helps to increase the components in the milk. So since the milk and milk components, we found an increase, it was pretty obvious that we would find a linear effect for the increase in the synthesis of fat corrected milk yield, or if the milk yield was adjusted according to the energy corrected milk yield. So you can see here, if you increase the metabolizable lysine as a percentage of MP from 6.5, where we have majority of the data, from 6.5 to, let's say, 8.5, 2 percentage point here, there will be a 2.4 kilos or roughly 4 pounds of increase in energy corrected milk yield in dairy cows. Unfortunately, we were unable to find an optimum amount. We were unable to find the quadratic effect for these response variables, which make the case that we really don't know what happens when we feed cows with a very high lysine-based diets, like let's say 9.5 or 10% of metabolizable lysine as percentage of MP. Probably this much is not needed. Probably we need more. We really don't know, because we couldn't find a cut point where the response was maximized. Interestingly, we found an interaction between metabolizable lysine as a percentage of MP and metabolizable methionine as a percentage of MP for feed efficiency. It doesn't matter if you evaluate feed efficiency based upon FCM over DMI or based upon ECM over DMI. We found the exact same interpretation of the data. So here, there is a little bit change in the graph. So we found this presentation pretty easy to understand. So here we have 5 different levels of metabolizable lysine represented by different symbols and different lines, and this is the range we selected based upon the range that we found in our data set. So we had experiments with 5.1 to all the way to 9.2% of metabolizable lysine as a percentage of MP. And similarly, on the x-axis, you can see here the experiments that we had in this analysis. They ranged somewhere from 1.8 to 2.9% of metabolizable methionine as a percent of MP. So you can see here, when we had experiments where we had pretty low methionine as a percentage of MP, let's say 1.8, but we feed them 7.4% of lysine as a percentage of MP. The efficiency based upon FCM or ECM, it was close to 1.46. But when we increased the amount of metabolizable methionine as a percentage of MP in the diets of cows, you can see here the response to supplemental lysine was greater, and it happened in both cases. So suggesting that not only lysine but also dietary methionine is also crucial to increase the efficiency of those cows. So one of the objectives of this meta-analysis was to determine the effects of supplementation of rumen-protected lysine on different concentrations of essential and non-essential amino acids in blood. So in this particular table on the left side, you see different essential, non-essential amino acids. And then we are providing here a list of different treatment means, a total number of treatment means and experiments that contributed for this analysis. And then we estimated the least square means and standard errors of means for concentrations of amino acids when cows were fed either 6.5 or 8.5% of lysine as a percentage of MP. Obviously, cows were not fed that. We use these two numbers to estimate what happens if you feed 6.5 versus 8.5. right? So you can see here an increase of lysine as a percentage of MP from 6.5 to 8.5. It was quadratically associated for the arginine, but it linearly increased the concentrations of lysine in blood, which were pretty much expected. But on the other hand, the concentrations of methionine, they were linearly reduced. And also, we found an interaction for total essential amino acids between lysine as a percentage of MP and methionine as a percentage of MP, suggesting that if the diets were in the postpartum period had increased level of methionine, there was a reduction for the total essential amino acids. So collectively, the supplementation of amino acids, it changed the profiles of different essential and non-essential amino acids, which makes the point that this dietary intervention it facilitates the mobilization of amino acids, which might be beneficial to explain the physiology of what we observed in this meta-analysis, that cows gained a little bit of body weight. So somehow those amino acids were partitioned for the accretion of body tissue in compared to those diets when the lysine as a percentage of MP was reduced. So finally, the conclusions from this meta-analysis are supplementing lysine as rumen-protected lysine starting during the postpartum period. It not only increased the blood concentration of lysine, but when the supplementation was started in early lactation or for an extended duration, it resulted in 1.51 kilograms more milk compared to non-supplemented cows. Also, increasing lysine as a percentage of MP from 6.5 to 8.5, it linearly increased not only yield of milk, but also milk components without a concurrent increase in dry matter intake. And response of feed efficiency was influenced by postpartum metabolizable methionine. As you feed more methionine in the postpartum diet, the benefit to the feed efficiency was greater as compared to non-supplemented cows. Unfortunately, we were unable to find the optimum amount of supplemented rumen-protected lysine because we observed the responses were increased up to the 9.25% of lysine as a percentage of MP in multiparasitatic cows. There were some limitations, or I would say there are some future directions which can be extrapolated from this meta-analysis. One of that is this data was analyzed in multiparous cows, and we know that nulliparous represent roughly close to 30 to 35% at a farm. So we really do not know what happens when nulliparous cows are supplemented with rumen-protected lysine. Second thing was the information on effects of supplementation of rumen-protected lysine on the health of those cows was not available in the literature. There has been some work from University of Illinois and some other groups, which shows that rumen-protected lysine improves the immune function in dairy cows, but certainly this has to be validated using more experiments. And also, we still need a large dose titration experiments to understand the impact of lysine as a percentage of MP beyond 8.5 or 9.25 in the diets of lactating cows. At the end, I would like to acknowledge my major advisor, Dr. Heather White, at the time of my postdoctoral fellowship in her lab at University of Wisconsin-Madison, which not only sponsored my fellowship, but provided great insights to finish this project. Special thanks to Francisco, who has been instrumental in suggesting in giving great feedback during the statistical analysis, and obviously the Dairy Innovation Hub, which funded this project so that it happened. Thank you so much. If you have any questions, I would try to be there. I think Dr. Heather White will be there to address the questions, but in any case, I'm providing my email address here for any questions. Thank you so much.